All right, so lecture number 4, we're going to continue with mathematical modeling. We covered modeling in time domain, and so we're now going to look at a different type of modeling. It's called state space. So in this presentation, we're going to look at a new type of modeling called state space modeling. And we will not go too far into this presentation today because you're just coming out of a test. And so I'll pick up on the rest of the presentation next week, all things being equal, all right? So the other parts in the presentation will include deriving models in state space to transfer function conversion, and doing conversion from transfer function to state space, all right? So let's start with the basics now. What exactly is state space modeling? So we need to recognize that feedback control is one word, feedback is one word. Feedback control design and the analysis, you can approach it from two different perspectives or two different domains in particular. So you could do your modeling in what we call frequency domain, which is the Laplace transfer function type representation, or we could do our modeling in time domain, and in that domain, what we use is the state space model. All right. So in the previous lectures, we looked at transfer function, and transfer function speaks of the Laplace representation, and so that would basically be speaking to the frequency domain. So today's presentation is about the state space modeling. All right. But before we get into the state space, I want to just look at the difference between the two. So frequency domain, I will call the classical approach. It's the traditional approach. I mean, classical meaning, you know, it's a model that has been used in the early days of control system development. Right? It has its limitation. It's very simple to use, but it has its limitation in that it is limited to linear time invariant systems. That's one. And you can only model single input, single output systems, all right, SISO abbreviated. So when we speak about linear time invariant systems, we're speaking about systems whose model does not depend on time. Let me be clear on that. The model is not time dependent, which simply means that if you model the system right now, 10 minutes from now, 2 days from now, a week from now, the model will still remain the same. You might ask, how comes? How are we able to have these changes? A very good example to look at is the model of an aircraft. So aircraft, we're modeling the aircraft in terms of the entire unit. Now, in modeling the aircraft and its movement, its mass would have to be taken into consideration in that model. Now, you can appreciate that the mass of an aircraft on departure is going to be different than its mass on arrival at its destination. Reason being, it is consuming a significant amount of fuel. So therefore, we would say that that system, the model for that system rather, is time varying. Yes, it's time varying. That means the model will change with time. There are other systems that will exhibit similar features, all right? So frequency domain cannot address systems like that. State space model, on the other hand, now, which we call the modeling approach, can be used to analyze any type of system, including nonlinear system, time varying systems, multiple input, multiple output systems, they call them MIMO. Any system at all you can think of, you are able to derive a state space model for that system. All right, so state space model is superior in terms of the type of systems that you can model. Now I'm going to discuss the concept of the state space model. So when we are representing a systems model or representing a system in state space model, we are using two equations to do that. All right, two equations to do that. We are using an equation that is called the state equation, and we are also using an equation that is called the output equation. And the format that is shown on the slide here is the format that is actually utilized. All right, so the state equation and the output equation, two equations. So anytime you're going to see a state space model, expect to see two equations of this format. Now what we have here for the state equation is that we have x dot is equal to a times x of t plus b u of t. That's the state equation. The output equation is y of t is equal to cx of t plus du of t. All right. Now let us make sense of the two equations by appreciating what each of the terms represent. So for x of t, it's called a state vector. All right, so x of t is the state vector. X dot of t is the first derivative of the state vector. Y of t is the output vector, and u of t is the input vector. Now A, B, C, and D, they're matrices, and they represent respectively the system matrix, input matrix, output matrix, and the feed-forward matrix. Okay, now let us begin to further explore what exactly the state space model is about. First of all, let us describe what are state variables. So state variables are the smallest set of linearly independent system variables, such that the values of these variables, yes, at time t0, along with the input variables, will completely determine the behavior of the system at t from t0 onwards. All right, so you're able to describe the system behavior from t0 onwards. In a nutshell, what does this mean? It simply means that if there exists a system that we call system A, right, there's a system that we need to model. There is a thing called, or a vector called, well, let's call it a state variables, okay, which is the correct term, state variables. There are a set of state variables. These are variables that describe the state of the system. Now, the word state here is not a special word. I could ask to define some states about your laptop you're using right now. You could look at its temperature. That's one state. You could look at its screen light intensity. That's one state. Okay, so the term state is not a special term, but it's just simple the state. Another example, you're looking at a electric motor. What do you believe would be some of the states of that motor? Somebody just go ahead and comment on that question. What do you believe would be some of the possible states of that motor? Yes, go ahead. Are you with me? Go ahead, Bruce.
Yes, but we don't get the question. Don't understand the question, basically.
We're trying to appreciate the term state variable. All right, thanks, Bruce. State variables. And I am saying to us here that when we're describing a system, there is a set of variables called state variables. Now, I want us to appreciate the term state variable without going into the full definition here again. And I'm saying state here is not a special term. Okay, it is simply referring to the conditions, and it has to be a function of time. So I asked a question just now about an electric motor. What would be sort of possible states of that motor? You could talk about the motor's current. Bruce, go ahead. Sorry, Burns.
No.
Steve?
Yes, I was saying that would the angular velocity be considered one?
Absolutely. The angular speed, yes, or
Right.
velocity, if you wish to put it that way, because it could have gone left or right, certainly is a state. The armature's current could be a state, and there are other things. We're just simply talking about some of the things that are associated with the condition of the system. Okay. Now back to our definition for the state variable. It says it is the smallest set of linearly independent what? System variables. Again, let me step back from this definition and go ahead and give you a scenario. It is not uncommon for us to make judgment of a person's response. Right now, if you think about it, you may have a friend or a family member where if you said, okay, let me create a situation right now. If you're in the bank and somebody simply walk before the individual in the line and stand up and just behave as if everything is okay, what would you predict that their output response would be? No, you might find that there is one person that you know who would turn the bank upside down if that ever occurred. And how did you come by that judgment? Based on certain characteristics that you are aware of the individual. So the individual might be very short-tempered. That's a characteristic. The individual might be very to the point, or very blunt, so to speak. And so that, along with other characteristics, and by the way, the characteristics must overlap. Say the person is easily angered and the person is short-tempered. Those are similar things. Okay, that's just one case. And so you would say, based on what I know about this individual, it is very likely that this individual will definitely respond this way. So what we're doing here is to use some characteristics that we know of the individual to predict the behavior of the individual in a particular scenario. You follow what I'm saying? So in a similar way, what we're saying here for a system, there exists a certain set of linearly independent variables. You want the minimum set. So tell me the minimum number of the minimum characteristics. Just give me the minimum. Don't give me everything. But there exists a minimum number, the smallest set, that if we know these values of these state variables, yes, along with what? Along with the input, we can do what? Completely describe the behavior of the system from T naught, that initial time at which we know the state variables, onwards. Those are our state variables. Now, it is the state variables that when you put them together, they are called the state vectors. We put them in a particular format and we call it the state vector. So the state vector consists of the state variables. Okay, is that okay? Now, the state space model, it's important. The state space model is not unique. It is not unique, but it depends on how the state variables were selected. Okay, it depends on how the state variables were selected. All right, and I'm going to show you in the next example, in the example that we'll do, how this is at how we obtain this outcome. So here we have a network, electrical network, and we are seeking to derive a state space representation for the network. It's a RLC network. And we are defining the output of our system, and this is the resistor current, IR of T. Of course, the input is the source voltage, okay? Excuse me, source voltage. So here is the suggestions that I'm presenting for achieving or obtaining the state space model. 1, we're going to label the branch current. 2, very important now, we're going to select the state variables, and this is how we're going to do it. Well, first of all, we're going to write a differential equation for all the energy storage devices. Yes? So guess what? We're focusing our attention right now on selecting the state variables. And this is how we're going to do it. We're going to write a differential equation for the energy storage devices. And then we're going to choose the variables that are differentiated as the state variables. So let's now go back to the circuit for a while, just for us to recognize the elements in the circuit and determine what our energy storage devices are. So you should recognize that we have 2 independent energy storage devices, the inductor and the capacitor. So we're going to now proceed to write a differential equation that describes the relationship between the current and the voltage for these 2 devices. So equation 1 is addressing that for the capacitor. So the capacitor current is equal to the capacitance times the rate of change in the capacitor voltage, that is the derivative of the capacitor voltage with time. And for the inductor voltage is equal to the inductance times the first derivative of the current through the inductor. Now, the statement says, choose the variables that are differentiated as the state variables. Let me take the question from Burns.
Yes, sir. I was just wondering if there is a specific rule to follow when choosing the subject of the formulas. So,
What? I'm sorry, what formula are you referring to?
Formula 1 and 2. I'm saying that why is it then, for instance, Formula 2, current wasn't the subject of the formula.
Current, not the subject. All right. If I understand your question clearly, well, I'll answer it in this way. What we're seeking to do is to write a differential equation that describes the relationship between the current and the voltage in the network. Now, listen carefully. We're writing a differential equation. If you go ahead and make current the subject, would it be a differential equation?
Okay, sir. Understood, yeah.
All right, so you will see why we're doing it this way, all right? But your question is noted, thanks. So having done that, we are now going to select our state variables. And we're selecting the state variables as the variables that are differentiated. So you should recognize that in question 1, in equation 1, what we are differentiating is the capacitor voltage. So therefore, we're going to label that as our first state variable. In the second question, in the second equation, we're differentiating the current in the inductor, IL. And hence I'm selecting x1 to be VC and x2 to be IL. Now, this needs to be noted that the number of state variables, yes, is equal to the number of independent energy storage devices, right? So here, the question could be asked, how do we know that we are going to have two state variables in this equation? A simple answer is based on the number of independent energy storage devices. All right, we'll discuss that a little bit more, energy storage devices, as we continue in other examples. We're now at the third step. The third step says express IC of t and VL of t in terms of state variables. All right, so let me bring you over, and this is where I would need to need some space to write. So let me bring back your attention to where we're going. Whenever you're doing a question, it is important to know where you're going. It's important to know your destination. What is our destination? Our destination is, and I'm going to have to go back with my slides, is to end up with an expression that looks like this. Okay? That's where we're going. Now, you remember the second rule that says select the variables that are differentiated as our state variable? There's a reason for that. Look at what is going to be happening. I'm going to attempt to write here. Okay, note the expression and formula. I'm going to go back to my slides. Okay, but note that what we're expressing in the first equation, that is the state equation, is what? The first derivative of the state vector. That's what the thing is. So if we go back to our problem, we say, okay, let's see how that supports what we're doing. Let's see how the selection supports what we're trying to achieve. So we're going back to insert a slide here. We're going back to the question. So if we look at this, right? Look carefully at the two equations. Remember what we want. I'm going to write the first equation out. We want x dot, which is the derivative, all right, of the first, I'm sorry, of the state vector. That is equal to, we don't know yet, but we know the format, right? But right now, our attention is on what it is that we want. We want the first derivative of the state vector. And it is equal to, we don't know yet. But we are aware that the format, and I'm going to now write the format, is equal to A times X plus B times C. I'm sorry, times U of T. All right, let's get that clear. So it's X dot is equal to A times X, and X is what? State vector, plus B, which is a matrix, times U. I wish I could erase the U by itself. U, which is the input. All right. So when I said, go ahead.
One of the x's represents state vector and one represents a state variable.
No, man, I did say it, you know. Wherever you see the x, it represents the state vector. What does this represent?
Oh, the first derivative of the
Correct.
state.
Correct. All right, that's the first derivative of the state vector. It's equal to a matrix that we don't know yet times the state vector plus B, another matrix, times the input. All right, good. So what I'm trying to get you to appreciate is that if you select the state variables as the terms differentiated here and here, we are already on our way. We are already on our way to achieving this. So if we put this constant over the equal sign over here, this here, don't you see that it's now resembling this, the first derivative of the state variables? So let me write this another way. X dot is equal to what? X1 dot, X2 dot. It's the same thing. We'll be able to see this. So what did we say X1 again? X1 is VC of t. There we go. We're differentiating VC of t here. So on the next slide, what you're going to see is the arrangement of the equation that will make dVC of t dt the subject, and also dIL of t dt the subject in the second equation. But in addition to that, we have to make a number of substitution. Why? What we're saying is, if we know the state variables along with what? The input. So the only two things that we're going to use to define the model are the state variables and the input. Note, see them here? State variable, input. Therefore, the equation that we're going to be writing next will only have these variables in it. If they don't, you have to substitute. So let us proceed. So when we see if we could do this here now. What we had before, let's go back. I wish I had the space. So look at what's going to happen when we move the C over. It's going to have IC over C. Move the L, we're going to have VL over L. But we have to replace IC because IC is not a state variable. Note the state variables, right? Note the state variables, VC of t and IL of t. Both of them, they're not state variables, so we have to replace them. Question is, what do we know about IC? All right, and that's what we're going to do in the next slide. So we know that IC is equal to IL, and it's also, I'm sorry, IC is equal to IL minus IR. Now, the challenge with this is that we don't have the circuit simultaneously to look at. And this is what's going to now give me some homework to do in terms of how to bring up a whiteboard slide at the same time. I did promise that in another lecture, but I'm going to get through this tomorrow. But long and short, I have to go back to the circuit so you can appreciate why it is that IC is equal to IL minus IR. I'm going to do that quickly so you can just appreciate that. All right, IC is equal to this current here, IL minus IR. Okay, so we can appreciate why we have it looking like that. That's according to Kirchhoff's current law. Okay, so having written that, we again re-examine our equation. What do we find? We find IL. Let me first of all ask you, do you remember what the state variables were? But remember, VC and IL. All right. I'm sorry. Let me show you what it is, since you're perhaps not remembering. Again.
Yes, sir.
VC and IL. Those are the state variables. Okay. So let's continue. So what we're saying, and I just lost my notes. So X1 VC, X2 IL. So now come back to here. We substituted for IC and we have IL minus IR. Look at the two variables. Do we have state variables only there? Answer is no. Of the two variables there, only one fits the bill, IL. Therefore, we now have to do what? Make a substitution for IR. Okay. What do we know about IR? Because the capacitor and the resistor are in parallel, both of them would have the same voltage up across them. Hence, we can remove or replace IR with VC of T over R. Okay. Now, we re-examine the equation. Again, we know that IL is satisfied. Let's look at VC over R. Absolutely. The variable here is VC, and it is actually the first state variable. So yes, the equation is now in an appropriate format to represent that aspect of the state equation. And so we can now proceed to the second part of the state equation. Okay, so what we're going to know is that this part here is going to occur here, as you can see. Now, VL is not a state variable, and hence we need to replace it. VL occurred in the second part of the equation, right? So we have to replace VL. The question, what do we know about VL? VL is equal to the source voltage, the input, minus the capacitor voltage. Again, similar to how we examined the first equation, we're going to do it for the second one as well, this one here. We're going to ask ourselves the question, is V of T a state variable? In fact, I should be asking it this way. Is it a state variable or is it an input? Because we can only express these variables or these terms in terms of the state variable and input. Right? I have to bring it back to the fundamentals that we're expressing this equation in terms of state variables and input only. Okay? So we're asking the question, is V of T a state variable? The answer is no. Then we ask the question, is V of T the input variable? The answer is yes. And so V of T would qualify as being an appropriate variable in the expression. Let's move to VC of T. Is VC of T a state variable? The answer is yes. Right? It's actually the first state variable. Hence, it's now qualifying to be substituted into the expression here. So now we would see that we have just expressed the, let's bring this up here, the two equations in terms of state variables and inputs. All right, so we're seeing equation 5. Yes, remember what we're going now. We're going here. This is where we're going. X1 dot X2 dot equal to, and we're seeking to address that. Of course, what we're actually working out, are the matrices X and I should say the matrix X and the matrix B. That's what we're seeking to find, because we already know what the state vector is, and we already know what the input is. So our task here is to find the matrices A and B. Okay. Now, this is the part that would take some close inspection. Again, it would be very nice to have a separate whiteboard, but in the absence of that, let me try to proceed. Let's look at the equation here. Let me remove this one. So remove. What we're seeking to address is to determine or to substitute the term. So what exactly? Let us write back what we know. Do you recall what X1 was? X1 was VC of T. X2, VL.
Sir, VL?
Go ahead. Go ahead.
Thought X2 was supposed to be not a variable.
IL. I'm sorry, IL.
Okay.
Thank you very much. So let us now go into equation 5 and substitute. So I'm going to try and take this here now carefully. The space is very small. X1 dot is equal to, we're not going to put back what we see there, but we're going to just put back either X1 or X2. So look carefully at the first part. What is that? IL is what again? IL is x2. All right, IL is x2, but I'm going to do it in a particular way. I'm going to put x1, x2, and I'm going to put u. For x2 dot, I'm going to do the same thing. x1, x2, and u. So it now leaves us to put in the coefficients. So let me ask the question a different way. Go back to equation 5. Yes, go back to equation 5 and tell me if there is an x1 term in the equation. Remember, x1 is VC of t. If it is there, tell me its coefficient.
-1 over CR.
All right, so -1 over CR. All right, that's the coefficient of x1. Why do we do that? X1 is what? VC of t, and that is the correct response. All right, -1 over CR. Let's now move to x2. What is x2? X2 is IL. Is there IL term inside here? Absolutely. What's the coefficient? 1 over C. So I'm going to put plus because a positive term, 1 over C. How about the input? Input is, I think it's what? V of t. V of t, right? So
Yes,
input
sir.
is, remember, U is equal to V of t. Is V of t an expression? Answer is no. So what do we do? Put plus 0 U of t. Let's continue. Let's go to the x2 dot, the first derivative of the second state variable. And we are going to focus our attention again now on this expression. We just did this one here a while ago. Okay? We just did that. So we're going to do this part. Okay? Now, what is the coefficient of x1 in equation 6? Again, you must answer the question. What is x1 representing? It's representing VC. So go ahead and tell me what's the coefficient of x1.
-1 over L.
All right, thank you. That's -1. And my pen stopped. Oh, shucks, my pen just went down. -1 over L. Oh my God. Let's try this again. -1 over L. There it made the bad writing. What's the coefficient of x2?
0.
Right, because x2 is IL and there's no IL term in the expression. Therefore, we're going to put plus 0. How about the input? Is there an input term in there? VC, I'm sorry, V of t?
Yes, the coefficient for
says
V
yes.
of t would be 1 over
Is
L.
correct. 1 over L.
Sir,
Go ahead.
you can go over when we get to the term that x2, the coefficient of x2 is 0.
What is x2 representing? You recall? X2 is the second state variable. Remember, CTR put it here so you can quickly look at it. X2 is IL of t. So when I say, what is the coefficient of x2? I'm talking about the coefficient of IL. So when you look at each equation, you're going to look for IL. If IL doesn't exist, therefore its coefficient will be 0.
So what you have up here? So you have V L IL you have up here. So isn't that x2 equal V L of t?
All right. I apologize again. I can't erase it by itself. This particular platform, when I press the erase button, everything goes. This is
Okay.
IL, and it was pointed out earlier. I put V of t for VL of t first. It's IL. Okay, so bear with me. Inductor current. Okay.
Okay.
So we're looking at each expression and we're looking for each of these terms. X1 is VC, X2 is IL of t. Okay? And wherever we don't see these terms, the coefficient is 0. Other than that, we need to extract properly the coefficient, bearing in mind the sign of these coefficients. Now, if you're able to observe, if you need to expand your screen, you'll recognize that what we can now do is to extract the coefficients of this entire section here. I don't have enough space. We could take out, I'm going to attempt something here. It's going to make it a little bit more messy. Look at this point here. Whatever we have here can be factored out. So we look at carefully, we see that there's a minus 1 over CR. It's here. There's a 1 over C, it's right here. There's a minus 1 over L, it's right here. And there's a 0. What's happening? When we're doing vectors and matrices, we can extract the coefficients. And if you look carefully, look at this, row by column. This element, or this term, sorry, times x1. If we expand the matrices, we're going to get 1 over RC times x1. There we go. Row by column again. So 1 over C times x2. There we go. Plus 0 times U. There we go. How about for down here? We go to the second row in the A matrix. 1 over L negative times x1. Here it is. 0 times x2. There we go. Plus L times, 1 over L times U. Here we go. So what I've just shown you here is how you would take the expressions 5 and 6 and extract the state equation. Okay, we're not yet done. We have just evaluated one of the two variables. The second one is the output variable, and that's easy. Output is equal to, we say y is equal to the output, whatever the output is. Now what's the output? The output is simple V of t. Simple V of t. No, I'm sorry. It's the current in the resistor. Did you say that? Current in the resistor. Now,
Okay.
it's IR. Let me fix that. I'm sorry, IR. Okay, so it's IR. And we went through earlier about substituting because IR is not a state variable. So I'm going to erase this, please. Please bear with me. Once I press erase, everything goes. So y is equal to IR of t. IR is not a state variable, so I have to substitute. I did it before. It's equal to VC of t over R. VC is a state variable. So again, to do the expression, we have to do something similar. Y is equal to, and we're going to put x1, x2, and u. What is the coefficient of x1? X1 is VC, therefore it is 1 over R. What's the coefficient of x2? X2 is IL. There are no IL terms, so we're going to put 0. What about input term? No input term, do we? So put plus 0. So now putting it into the matrix format, we can extract the terms. See them here again? 1 over R, excuse me, for x1, 0, x2, and the matrix that is supposed to be beside it, actually D is 0, based on the fact that U is equal to 0 here.
Okay, sir. So
if you yes, go ahead.
R1 over R 0 is actually row matrix then.
It is.
Column. Okay.
It's a row matrix, yes. And if you expand here, you'll get back what we have down here. All right.
Yes,
right. It's quite a bit in terms of having the space to expound on it, but I am going to ask that you review what has been presented in addition to other presentations, other material in books, right? And then next week we'll pick up from this point and go forward. All right. But before we go, any other question you want to ask before we close off?
Yes, sir. What I want to see what we can really work on that whiteboard thing so that
Yes, I need to expand because we need more space. Need more space. It's a different platform than the one I've been using before, and so I'm just getting a bit accustomed to it. I need a whiteboard in addition to the presentation screen. I may have to switch out the platform and then come back on, but I'll work on it for next sessions. All right, so that's it for the questions or comments.